Good morning, everyone. Good morning. Can we have a bit of a silence, please? I realized there was a couple of weeks break, but now we are back to the seminar series. Yeah? Today the seminar will be given by Hannah. Hannah comes from the Netherlands, Nijmegen, I believe, right? So you've got your master's there. Then she did her PhD in Hungary, in Budapest. Last week she was visiting her colleagues there again, giving a seminar, I believe on a similar topic than today. And now Hannah is with us as a postdoc for a little more than a year now, I believe, right? And today Hannah is going to be talking about yields, nuclear astrophysics, yeah, and yields of massive stars as dictated by asteroseismic constraints of interior structure. The floor is yours, Hannah.
Okay, I hope this is working. Good. So the presentation today will be more about context and understanding what's going on than my results, which are also very interesting, but I'd rather have you all understand what I'm actually doing than understand why I got what. So to start with nucleosynthetic yields. So basically, when we look at nucleosynthetic yields, we use three key ingredients. This is aside from the mass and the initial metallicity of the stars. We look at how do we produce the isotopes inside the star, which is nuclear physics. How do we move the isotopes inside the star? All kinds of mixing processes. This is stellar evolution. And then finally, we look at how do we move the isotopes out of the star, which is more on the stellar winds. And because massive stars are, one, big, they live fast, they have very strong temperatures, they have strong winds. This is why we look at massive stars in this context. So the first part is how do we produce isotopes? And for this we need nuclear physics. We look at nuclear reaction rates, which basically tell us how fast one isotope is turned into another at which temperatures and density. For simplicity, we generally forget about the density and only look at temperature. And so the nuclear reaction rates, they control the isotope production, they control the ratio between the different isotopes, and also they determine the duration of the burning cycles. So they control the lifetime of the star. And especially, this is an example of the CNO-cycle. The laser pointer is currently not working, so I can't point it out. There is the nitrogen-14, nicely in the middle. That one determines basically your main sequence lifetime of a massive star, because this is the slowest reaction, and this is why we need nuclear physics. We need to be careful what we put into our star, because otherwise we might actually get unphysical results. So for this entire project, we put 212 isotopes in the nuclear network, because we want to look at what happens inside, what produces what is interconnected, and to do this properly, we need a lot of isotopes. And for the reaction rates, we use the latest version of the GNR reaction rate library, though there are many different libraries out there that you could use. So now we come to nuclear astrophysics. And here is the periodic table. Because nuclear astrophysics is basically the study of nuclear level processes that occur naturally in space, combining nuclear physics and astrophysics. And if we look at this one, this is a very nice representation of 6 different potential sources of the isotopes. So we have Big Bang fusion, which mainly produces hydrogen and helium, a little bit of lithium. We have merging neutron stars, which is also known as the very fancy R process or kilonovas. You get all the heavy elements. We have dying low mass stars, which can be seen as HB stars. They produce carbon, nitrogen. We have exploding massive stars, supernova 1As, type 2s, producing oxygen. And then we have the exploding white dwarfs, which is a type 1A supernova, producing other things. So if we look at this, we kind of know where everything comes from. We can identify which source makes what. The only problem is if we then look at it a little bit differently, and this is again the periodic table, but this one has a little bit of extra information in the squares. So on the x-axis of this figure, each of everyone has the time in giga-year. From the Big Bang all the way to the origin of the solar system. And the vertical, so the horizontal lines, they represent the current abundances in the sun. And to understand where the solar system is coming from, we need to match those numbers. And for most of them, we do actually quite okay. So you can see we get all the hydrogen we need, we get all the helium we need. Beryllium and boron are very fragile elements. We don't know what to do with them. Carbon, we don't get enough, based on this study. Mind that there is different studies always. We get enough nitrogen, oxygen looks okay, fluorine, no again. We get a bit too much neon, and so you can go through the entire table. We massively underproduce gold in this model as well. So this is what we're trying to explain. And then but then there is also, these are the elements. But most of these elements have different isotopes. And that's when we look at this. So this is the nuclear chart, which is basically your periodic table stretched out. And for those who have never seen this, the black line in the center, those are the stable isotopes. This is where most of our normal elements are located. And the color indicate different kind of processes for the nuclear decay. So if we look at the Big Bang fusion, we're in the very bottom corner of the diagram. This is where hydrogen and helium are located. Then we look at stellar fusion, which goes up to the iron peak. This is hydrostatic burning. Well, we get to, well, not even a quarter of the chart. Next step, we do the neutron capture processes. And there's 3 of them, and they depend all on the different speed of the neutron flux, whether you decay before you capture your next neutron or not. In the slow neutron capture process, which stays fairly close to the valley of stability, you capture a neutron, you beta decay, you capture the next neutron, you beta decay again, and so forth, till you reach the top of the valley of stability. Then there's the next one, which people call the intermediate neutron capture process, which is same principle, just a little bit higher flux. Then we get the rapid neutron capture process, and this is how we get actually to the top of the chart. So the rapid neutron process is you capture a lot of neutrons, and then you start decaying. But now we've covered maybe half of the chart, because we're only at the bottom half now. So at the top half, there is something that's called the proton process, which is more like a disintegration process, which starts at the top and moves down. If you look from it from the other side, people call it the gamma process, because these are all P-gamma reactions. So it could also be like photon capture, but that's just strange to think about, so people just call it the proton process because it goes down. And then there is a few other processes in that area that involve neutrinos, and then it gets horrendously complicated because neutrinos are also not very well understood. So I'm staying far away from that. I'm sticking safely with stellar fusion and hydrostatic burning. So the next step then is, how do we move the isotopes in a star? Because we now know how to create them. Nuclear physics tells us. But now, how do we get them from one place to another? Because most isotopes are produced in the deep insides of the star. But to get them into the interstellar medium, we need to get them to the surface. So for this, we need mixing processes. And these are fairly simple to separate into 2 categories. We need mixing at the convective boundary, and we need mixing in the envelope of the star. And for the project, we use the Ledoux criterion for convection, it doesn't matter that much, makes a small difference compared to Schwarzschild. But most importantly, here we use asteroseismically inferred values for the convective boundary mixing and the envelope mixing. So we want to see what this does. Is this different from what stellar evolution theory has taught us up to now? And the last part is how do we move the isotopes out of the star? And this is mass loss, which can be stellar winds, which can be supernova explosions, which can be binary interactions. And in this case, we're looking mostly at the stellar winds. So everything I'm presenting here are wind yields. It will explode eventually, maybe, depending on the structure of the star, but we're not looking at that. So now I have to go here to go to the next slide. So what is then the connection to asteroseismology? So everyone here should know that asteroseismology is the study of the internal structure of stars by means of their oscillations. So the stars will tell, they will tell us something about the inside of the star. And so here, very schematically, let's see if the laser, oh, it works, great. Very schematically, the inside of the star, so this is the mass coordinate, here's the inside of the star, here's the surface, and here we show the amount of mixing in different types. So the important part here is that based on observations, from the asteroseismic observations, stars have larger convective cores than standard evolution, stellar evolution models predict. All of your stellar burning happens inside your core. If you have a bigger core, you get a different way of nucleosynthesis, you get different yields. But the question is, how different are they? So if you look here, so this area is the stellar core, this gray area. The blue area is the transition area, and then this is the stellar envelope. And what we've done is looking how can we solve this difference. So we make use of calibrated convective boundary mixing, which happens over here. In our case, we use the most simple way of convective boundary mixing, which is step overshoot, where we basically just extend the convective core by a certain amount, which is controlled by this parameter alpha. And then we also use calibrated envelope mixing, where the value is calibrated here at the bottom of the envelope, and here has this shape profile, but you can put in many different shapes. We just picked this one based on internal gravity waves. So basically what we did, we looked at a 20 solar mass star, which is nice and heavy, initial metallicity of 0.014, which is roughly solar, the nuclear network of 212 isotopes, and then we varied the overshoot parameter and the envelope mixing according to asteroseismology for the overshoot between 0.05 and 0.4. For reference, most stellar evolution models use roughly 0.2. And then there is different values for the envelope mixing between 0 and 6 on a log scale, which is generally not implemented in models unless you use rotational mixing. So these are some of the first results, and this is on the outside of the star. So now we look at the HR diagram. So what you see here is the more overshoot I add, the brighter the star will be at the end of the main sequence, and also it will be slightly cooler. And this, in our case, is advantageous because it increases the wind, because the wind is a function of luminosity and temperature. So and then here the blue line is the same over here, and here we vary the envelope mixing, and here you can see that for the first 4 values, the star doesn't really change that much. This is because the envelope mixing is a diffusive process. Diffusive processes need time. And the more massive your star, the faster it evolves, the less time you have. So only when you add quite a lot of extra mixing in your envelope, you start seeing the difference. And again, it moves up. Though while here it moves more diagonally, here the change is more vertically. Let's see. So more convective boundary mixing or higher envelope mixing leads to a higher luminosity at the TAMS, which is this nice little loop over here. We get lower temperatures at the TAMS, and we get higher luminosities on the Hertzsprung gap, which is this area where the star moves very quickly from this side to that side of the diagram. So now we look at the very inside of the star. So this diagram shows the central temperature versus the central density. And there is, for guidance, a bit of the different regimes. So this is the radiation-dominated regime. Here you have ideal gas. Here's the non-relativistic electron pressure. And we evolved all our models to a central temperature of 10 to the 9 Kelvin. So that is this line over here. And you can see that on the main sequence that's here, it doesn't change much. But as soon as you start moving from the main sequence to helium burning, which happens over here, you get a bit of a deviation in the central temperature. And here, especially here at the top at carbon burning, you can see that if the models with the lowest overshoot, they have already really started carbon burning and are almost done, while the models with the higher overshoot have need a little bit higher temperatures to actually start the carbon burning properly. And then here we do the same. So here we see also, but the biggest difference here is in the top area over here, where most of the models make this turn, but this model goes more or less straight ahead. And this is because at this point we transfer from convective carbon burning, where there is a convective core and which is well mixed, to radiative carbon burning. And this basically tells us that we made a change in the isotopic mixture in the center between carbon and oxygen. Because now, apparently, we don't have enough carbon anymore to produce actually the convective core. And the interesting part for that is if you would go to explosive nucleosynthesis, the carbon-oxygen ratio tells you what's coming out of there. So altogether, we kind of change our star. So again, more convective boundary mixing, a higher envelope mixing leads to a higher central temperature at helium burning, which is here, and an earlier transition into radiative carbon burning, which according to the literature should happen around 22 to 25 solar masses instead of 20. So the big changes here are, this diagram shows the hydrogen burning time scale, and you can actually see that if we have more convective boundary mixing, we get longer, we have the alpha overshoot on the x-axis. So over time, more convective boundary mixing leads to a longer duration of hydrogen burning. But at the same time, a shorter duration of your helium burning. And this is because if you have a longer hydrogen burning, you get a more massive hydrogen depleted core or helium core. And then when you start burning helium, your core is heavier, so you need more, it burns quicker. So this makes complete sense. And also if we have more envelope mixing, this leads to longer duration of both hydrogen and helium burning, because in this case, in both cases, we can tap into the reservoir that's above the core. So while normally you would only burn what is inside your core, the envelope mixing gives us access to everything that's above the core, which means we have more fuel, so my burning lifetime increases again. But again, this is only mainly visible for the highest amount of envelope mixing. So, and here's the core sizes. So here you can see that more convective boundary mixing leads to, the convective boundary mixing leads to a larger helium core, and here a larger carbon-oxygen core. However, More envelope mixing also leads to a bigger helium core, but it gets a smaller carbon-oxygen core. And this is because this mixing is very present. We get more helium into our core, so our core doesn't have to be as big to support the star as in the case when you don't have a lot of mixing. So this is on the stellar evolution side. Now we go to nucleosynthesis. So we look at this isotope, aluminium-26. It's a radioactive isotope with a half-life of 0.7 megayear. And this isotope is very interesting to look at because we can actually observe it. So we can see it in the interstellar medium by its gamma decay. And we can see it in the early solar system when people grind up meteorites. They check how much magnesium-26 is in there. They find it's too much compared to what we expect. And this must be aluminium-26 that has decayed over time. And here we can see very clearly that more envelope mixing leads to higher yields, because these are the normal yields. Here is the envelope mixing. More convective boundary mixing actually leads to lower yields, which was not a result I expected. I thought, well, more mixing, more stuff. No, because apparently we have a longer main sequence. And the longer the main sequence, the more aluminium decays inside the star. And it happens that from this model over here to that model over there, we managed to increase the main sequence with exactly 2 half-lives of aluminium-26. So we lost some aluminium in the star. But to really understand properly how we get to these conclusions, I'm going to introduce to you one of the most useful diagrams of stellar evolution. If you know it, it's very useful. If you don't know it, it can look massively confusing. So we're going through it slowly. So this is the introduction to the Kippenham diagram. The Kippenham diagram gives you information on the inside of the star. But in its very basic, it's the mass coordinate from 0 to 20 at the top, and some measure of time on the x-axis. Now here I plotted the x-axis in megayears, and you can see, well, not much happens because, well, this is the end of the main sequence. So all of this in the diagram will be filled up by your main sequence, where honestly not too much happens. And the rest of the evolution is squished into this area of the diagram. So that's not working, so we came up with something better. But it makes it slightly more confusing for most people. So again, we have the mass. And now what we plot on the time axis is the time until the collapse, the log of the time until the collapse. And this means that your end of the main sequence is here, and the rest of your evolutionary phases get nicely stretched out so we can actually see everything. So, but now it's very empty. So, and you know Kippenham diagrams are generally very busy and complicated. So what do we do? Well, we start with convection. So all the green hatched areas here are now areas where convection is your main mixing mechanism. And to guide you a little bit, this convective blob over here is hydrogen burning. This one is helium burning. Then these here are carbon burning. Here, this little blob here is neon burning. These are oxygen burning. And here at the end, there's silicon burning. And here you see the other advantage of plotting it on this weird time scale is now all of our burning phases take up almost equal space in the diagram. So we can actually nicely see them. Because if I plotted them on a very initial time scale, you would have mostly seen hydrogen burning. And, well, silicon burning would have been like almost on this axis, and you couldn't see it. So first we have convection. Well, we used convective boundary mixing. Where is it? It's here. So the cyan areas here, here at top of the cores. That's your convective boundary mixing. Now, we said previously that I make use of the Ledoux criterion for convection. And there is also the Schwarzschild criterion. And there's areas where those two do not agree with each other. In this area, we get semi-convection. So the red parts is where you have semi-convection. Then we have one more that is called thermal halide mixing. Basically, thermal halide mixing is the kind of mixing you get when you have heavier material on top of lighter material, and it diffuses down slowly. This is often not plotted, but for completeness, we have it here. Also, you can plot other kinds of mixing mechanisms on here, like rotational mixing if your star would rotate, or anything else, what you want to put in. So, but now we can still see that the background of this diagram is generally also some kind of color, and now it's still white. So you can plot anything useful on the color scale, often like the energy production, which shows you where your star produces most energy, or, oh, I forgot this one. In our case, isotopes. And to give a little bit of an idea of where my stuff is, so there's the helium core. So the area above the helium core still has hydrogen, below doesn't have hydrogen. Same CO core, here there's helium, here there is no helium. Oxygenean core, here is carbon, below here there is no carbon, roughly speaking. So, and then we plot something on the color scale. So in this case, helium, so I said, no helium below this line. Well, there's no really helium below this line, unless here in the end, because there you get disintegration of your isotopes and you get your alpha particles back. So here we can see helium. So we can see it very prominently present in the star at all times. But you can also see that the color becomes less bright in this part, and then it's gone. So you can see it's burned. So this is how we use these diagrams to tell us where is my isotope, where is it moving, does it make do my results make sense compared to diagrams? What does it tell me anything? So here I plotted aluminium. Well, so aluminium itself is radioactive. So when you look at the stellar envelope for this one, there is nothing present because radioactive isotopes are not primordially present in your star. So far, so good. But the other thing we can see is that it's produced. So there is a darker color and it becomes lighter as time progresses. This is because the material decays in the star. What then happens is that at the end of the main sequence, you get your convective envelope and it starts moving the material into the envelope, and then we lose the material. So this is how we lose the aluminium-26 to the interstellar medium. Also, we can see that it's very quickly destroyed in helium burning. So there's some aluminium present here, but in helium burning, you get neutron captures, and all of a sudden, your isotope is gone. There is some production here, but this is too deep into the star to ever see the surface. And there is some production here in the hydrogen burning shell, which also does not reach the surface at all. Now for this one, we have a higher amount of envelope mixing. You can immediately see it. So here the color gradient fills up the envelope. However, it does not really reach the topmost part of my star. So this explains why the yield from this model to that model increases, as we could have seen in the original one. So this is why Kippenhahn diagrams in my field are very useful. I hope you got a little bit of how they work now. So next isotopes we look at the chlorine and calcium. These are both also radioactive. These are produced in helium burning. So while aluminium is produced in hydrogen burning over here, these are produced in helium burning, which is this blob. And then what we see is that basically for most of the models, we get as good as negligible yields. This is 10 to the minus 19, which is very little. However, as soon as we add a lot of envelope mixing, you can see we end up at the top here, and we get actually quite appreciable yields. So more convective boundary mixing in this case leads to comparable yields over the whole line. However, if we add more envelope mixing, then we get strongly increased yields, and this is about 11 orders of magnitude, which is quite nice. So that's what you see here. Get the increase. Let's see. So here again, we look at the given diagrams. Again, nothing present at all in the star. At the beginning, this is calcium 41, yeah. Not 36. Don't know if that exists. So we have nothing present in the star at the beginning, as we would expect. Again, radioactive isotope is not primordially present. It gets produced here, you can see very nicely, and then it gets mixed out. But in this case, you can see there's basically nothing in the envelope, so it's not surprising we get a yield of 10 to the minus 19 solar masses. This one, however, you can see it's produced, and then it gets mixed out. However, here we see the effect of that the envelope mixing is diffusive, because while it is mixed out, the time scale is such that basically all the material gets mixed out to about here, and not everything reaches the surface. However, we have enough enhancement in the envelope to actually get a yield that is actually a bit of a valid number. So, yes. Then we also look at some stable isotopes. One of them is fluorine-19. Fluorine-19 is the only stable isotope of fluorine. The problem with this isotope is that it's also very easily destroyed. So it's very fragile, and therefore we basically don't know where it's really coming from in the grand scheme of things. So we're still looking at this one to understand how do we get the amount of fluorine on Earth if this isotope is basically so easily destroyed. Here again, convective boundary mixing gives a higher yield. And also if we have the maximum envelope mixing, we get comparable yields over the whole line. However, the initial fluorine abundance in the star is up here, hidden by the legend, the red line. So basically, these stars don't produce any fluorine, just destroy more, which is not helpful. Here on the other one is neon-22. Neon-22 is an interesting isotope because this is your main neutron source in your massive stars. So as soon as you reach helium burning, you get the neon-22 alpha N reaction. So we capture another helium core and we produce a neutron. These neutrons we need to produce the weak S process, which is the very earliest stages of the S process, which can be done in massive stars. So we look at this. Again, more convective boundary mixing gives a higher yield, especially for this one. And the envelope mixing has most effect for the lowest convective boundary mixing, because as you can see here, it has almost no effect anymore. Here we actually get one model with a positive net yield. The rest of them destroy more neon than they create. So here we have given diagrams at fluorine. This is always present, so this is why it's in the envelope. And you can see here during hydrogen burning, part of it is already destroyed. And this is why you get this empty band over here. Then during helium burning, it's partially produced, but also again destroyed. And then here in carbon burning, it's get destroyed even more. And here again, you see if you have more envelope mixing, this area becomes darker. you get the same band feature that was for the calcium, just a little bit less prominent, and the yield just goes up. So when we look at the stable isotopes of the CNO-cycle, we find that most yields are actually negative, except for nitrogen-14 and carbon-13. And also our surface abundances are only affected very late in the evolution. So here is the carbon to nitrogen ratio and the nitrogen to oxygen ratio given for different evolutionary stages. So this is at the main sequence, halfway the main sequence, end of the main sequence, on the Hertzsprung gap, and when we start helium burning. And you can see that only for most mixing we get a slight difference here at the Hertzsprung gap, and the big difference appears at the onset of helium burning, but this is not due to mixing, this is due to the mass loss, and we actually start seeing the inside of the star. However, we want to, observations of this ratio tell us that it should start changing earlier, so we have to look into this. And that brings me to already the last slide, very quickly apparently. So future work, lots to be done, will include a wider range of initial masses, because this was only 20 solar mass stars. To get the complete nucleosynthetic wind yields, we need to post-process these models, which is work in progress. It would be nice to add different mixing profiles, also mixing profiles that incorporate rotation, because these are massive stars. Massive stars in general rotate, but we ignored it for now. It would also be good to look at different types of wind prescriptions, see if that makes a big difference. We can test different reaction rates by using different input, and most importantly, comparison of the simulations and any observational constraints to see if we are getting closer a little bit. If we're getting a little bit closer to reality with our one-dimensional models. So this is about the end. So I hope you learned something, and thanks for your attention.
Thank you, Hannah, for an interesting talk and very nice explanation of the concept of the Kippenham diagrams. I finally start to understand what they mean. We have plenty of time for questions. Nico wants to go first, apparently.
Thank you, Hannah. Very nice talk. So I understand why the overshooting parameter is not well constrained, because you have this convection that comes into this radiative zone, and it's a very complex process. But the envelope mixing, that's just a diffusive process, right? Isn't that like very simple if you know the mass of your atoms that you want to diffuse and the temperature at which they have thermal motion? Or is there some other process that makes it that you have like quite a range in diffusive parameters that you want to test?
So the problem is that that would be the most basic diffusive process, but as you could see, there is sometimes the envelope turns convective. Then you get a different type of mixing. If you have, for example, rotation, you get all kinds of shears that add mixing, and in this case, what you see is that a convective core can drive what is called internal gravity waves, and these can also mix material. So yes, there is this very simple base diffusive mixing based on temperature and the chemical mixture. But on top of that, there is all kinds of different processes that also add. For example, like the thermal halide mixing, which you find when you have heavier material on top of lighter material. And you have to add all of this together to get your envelope mixing. So it would be nice if it would be so straightforward, because then we lose a lot of free parameters. But unfortunately, no. So, and also again, then the big issue is with many of these processes, they're three-dimensional. My stars are lines. You also have, it can also depend on how you fold your three-dimensional process into a one dimension, and especially with like rotational mixing, there's a lot of different ways to do this, and it all gets different results. So, unfortunately, not as straightforward. It would be nice.
Thank you. Right. More?
Hi, Anna. Great talk. I was just wondering, just as a follow-up to Nico's question, is it a fair conclusion for your work then that in order for these extra diffusive mixing processes, the shearing, the internal gravity waves, all that sort of stuff, would you say that it's a fair conclusion from your work that you require the net effect of these extra mixing processes to be 1 million times more than the typical temperature mass prescription in order to have a significant effect on the nuclear yields of the stars?
Well,
and is this reasonable-ish?
Well, in the case of, so the question is, obviously, we just applied what was on the main sequence also to helium burning. That's the first question. Can we also apply this to helium burning? That is what increases the yields. But at the other hand, yes, we do need this amount of mixing, one way or another, because we have constraints on the surface abundances. And currently, we don't match those.
So do the 10 to the 6 envelope mixing, they do in fact better reproduce real stars or expected yields or something?
Well, they start to get some enhancement of the changes in the ratios, but this is part one of future work.
Okay, cheers.
So part of this is we put in new parameters, and now we have to validate them. So that's the next step.
So Hannah, maybe to elaborate a bit further on this question, log DMX 6, is this something that is astroseismically observed, or this is just an extreme that you've arbitrarily taken in your simulations?
So this was the most extreme value to match models from, so my Pedersen, she looked at the sample of B stars, I think, and the 6 was the most extreme value she used, but there were actually a few stars that needed that value. So we just took the most extreme values from that study and chucked them back into our models. Okay. So this is, it's a parameter study.
Mm-hmm. Thank you.
I have a question with respect to the alpha parameter, whatever. Yeah. In your application of it, I can imagine it's in any boundary layer where you have a layer between convective, the transition region between convective and radiative, but it seems to play only a role at the core and not on the envelope. So not on any region in the star. If you look at the Kippenheim diagram, the effect on alpha seem to be important for the core transition region between convective core and envelope, but not on all other boundaries between convective region and radiative region. Is that is that physical, or is that just you applied it there specifically, or is it?
So basically, we didn't use what people call undershoot.
Yes.
So at the bottom of the convective areas, we don't apply it, and then we didn't use it on the shells.
And is that a reason for that, or is that
basically just computational?
Computational.
So the problem is that
there's no physical reason why it would be different on.
So there should be some overshoot, or there should be some convective boundary mixing also on the shells, but mainly because you can see it here. There is many little layers on top of each other, and then it becomes computationally a bit messy. So we did not apply it in this case.
Okay.
But most stellar evolution models will have some convective boundary mixing also on the shells. But again, the amount is likely way less than on the cores, because you still have the convective motions, and they're way stronger in the cores than in the burning shells. And there are studies on this, but we didn't get there.
Because in low mass stars, it is that region that is also subject to quite some discussion. with respect to S-process enhancement that we observe and so on. So it's not the core, because it's radiative, but it's the other boundary layer, which is subject to quite some discussion.
Hanna, you can correct me if I'm wrong, but another reason for ignoring undershoot might be because the idea behind the work was to test how astroseismic constraints on the main sequence affect the wind yields in intermediate and high mass stars. And undershoot is something that is astroseismically impossible to constrain for these stars on the main sequence.
Yes, so that's another reason indeed, but generally speaking, undershoot is also not applied. I think there's very few stellar evolution models that actually consider downward convective motions. Also because these convective motions depend also on the chemical gradient, and generally at the bottom of these convective zones, you have a very strong chemical gradient, and basically your convective block just bounces off it. So the undershoot should be very weak anyway. So why make our life even more difficult than it already is? Let's ignore this one.
In the low mass stars, it is the most discussed item to create the carbon-13 pocket.
Yes, but this is a massive star. We're staying far away from carbon-13 pockets, as interesting as they may be.
Thanks.
Hi. So one of the things that always interests me in these MESA models is how do I go from this to usable values with error margins? Because all these evolutionary models, by how they are designed, are a string of assumptions and trying to get values close to what we think they might be, and shaving off some of the complexity that you get if you want to do detailed studies only on this specific part, like let's say, for my case, winds. So what is the main thing, not the one that you've necessarily discussed here, but it's just like plugged into MESA that will influence your yields in the end? Can I look at these values as them being, even though we change the, I don't know, mass loss or whatever, one of the things you haven't discussed here, we change them by double factor, it will not change your values at all? Or do I look at these values and do I see them, okay, these are like vague regions where they could be, but if one of the assumptions is wrong, we get 2 orders of magnitude difference?
I wouldn't say 2 orders of magnitude difference, but what you can see in this figure, for example, we have, if you compare this one has a less strong wind, and here they actually compare quite nicely. No, this one has a stronger stellar wind, but it mainly matters on the, let me see, let's go to aluminium. So here you can see that we had a stronger wind on the main sequence, and our yields are actually a little bit higher. But it doesn't make a difference of orders of magnitude. But it does make a bit of a difference. It's definitely one of the other main uncertainties. But you can only put so many uncertainties in one model. You don't want to solve the entire parameter space. In this case, we looked at one aspect of the parameter space, which is the internal mixing. But as said, the nuclear reaction rates and the stellar winds, those are the other 2 main uncertainties what we have to deal with. But if you want to explore the entire parameter space, then it will be a lot of computational time. And in the end, I don't know how much it will tell you.
Yeah, no, I meant more like, is there one that we haven't discussed verbally here yet that might influence something, like deep into the trenches of MESA coding that nobody touches, that might be influencing your values heavily? If it's mostly the winds and what you've discussed, then great. Thanks.
So it is always in the complication is always in the free parameters, but the other problem is actually the solver itself. The way you solve the equations, that might actually also affect your stellar evolution, but that is inherent to the codes. This is why if you compare different stellar evolution codes, you get slightly different results because all the implementations are different. But that is also a big can of worms that I kind of don't want to open. even though it is good to be aware of this, I'm not going to touch that. I'm just sticking with one black box. That's enough.
All right, we have more questions about black boxes. Well, people are thinking, I'll have one myself. So basically, Hannah, what you showed is that log D mix has little to no role on the for the yields unless it's 6, right? And it seems like what we see on the screen, when you change it to 6, then you have this boost across the entire range of alpha parameter. And the only exception, or very noticeable exception, is neon 22, where you see the predictions moving in sort of in anti-phase, right? So why is that?
This has to do with what is present where and when. So for the radioactive isotopes, it increases because it is not primordially present. Neon 22 is present all the time. It's already there in hydrogen burning, and it gets destroyed during hydrogen burning. And if you then have a longer less overshoot, means you move less of your neon from the envelope into the core. So you get less destruction on that side. Also, these ones had the longest main sequence lifetime, so you have the longest time to diffuse all your saved neon up to the surface. So it's a bit of in most of the yields, it's a very complicated interplay between the diffusive timescales, so the burning timescales, what was present when. So when we look at the, for example, with neon, you won't see it become lighter over here. And here you can see it very slightly. For the fluorine, you can see that there is a color gradient going up. So for more envelope mixing, we actually start destroying more fluorine in the envelope compared to the non-mixing one. So this is where all kinds of different effects start to communicate with each other. And in the end, because this one is only partially destroyed, well, this one is completely destroyed, or, well, this one is more significantly destroyed than this one, you get this counter effect, yeah. So it's a combination between where and when it is produced and the duration of the different time of the burning cycles.
Yeah, thank you. Last call for questions. Yep.
My question is actually about this slide itself. So neon 22, as you mentioned also, is quite important for the weak S process, right? So given your results, would you say then that we need very efficient envelope mixing to also then have efficient S process?
So the weak S process mainly depends on the amount of neon you have in early helium burning. While the yield here is mostly the primordial neon 22 that you get out of the star that survives hydrogen burning. So they're a little bit decoupled. But yeah, so the more neon 22 you have, the more neutrons you might produce. So there is a slight difference. I think I looked at the neon 22, but also part of the S process happens in the explosive nucleosynthesis, and that's what we didn't look at. But then the surviving amount of neon 22 matters, and this is the wind yield, and not what is inside the star. So to make some assumptions or to make some guesses on what happens to the S process, you would have to look at the amount of neon 22 left at the end of helium burning.
Okay, thanks.
The second last call. Okay, no, let's thank Hannah again. hope to see you next week. Thank you.